So today we are looking at lesson 4-8. It's over the complex number system. And we're going to just start with a little bit of vocabulary. So basically, somebody decided to be able to take the square root of a negative number, even though we can't. So complex numbers are all based around taking the square root of -1. And so I, for imaginary, represents the square root of -1. So we don't actually write the square root of -1, we write I instead. So it looks like a variable, but it's actually the number square root of -1. Also, if we square I squared would be square root of -1 times square root of -1. So you can also look at I squared being equal to -1, because a radical times itself gives you the number underneath the radical. And we'll get more into powers of I here towards the end. So an imaginary number is any number in the form of, and then here's what's called standard form, A plus BI. So A represents the real part of a number, and BI represents the imaginary part of a number. So if I gave you real numbers associated with this, it would look like something like 2 plus 3i. So this is called a complex number, and so your definition for complex numbers here, it's just the set of real numbers and the set of imaginary numbers now put together. So this whole thing is called a complex number. It is in standard form. So standard form of a complex number is fairly picky. You have to have the real part of the number first and then the imaginary part of the number second. So we really can't write it 3i plus 2. It needs to be written 2 plus 3i. And so this is our real part, this is our imaginary part. So if you have a number that's just pure imaginary, it means that A has a value of 0. So if I had 0 plus 3i, so if this were 0 plus 3i, we would just have 3i. So that means that you will be left with just the imaginary part of the number. There would be no real part being added in front of it. Same thing can be said about a pure real number. Well, that's what you've been used to dealing with. So if you don't have this, if this is 0 here, you wouldn't have 0i. You would just have the 2. And so that would be considered a pure real number. If you just had this, a pure imaginary number. Then we're going to do some graphing in the complex number plane. And so it's a plane, and if you look down here, it's a plane that is very similar to the coordinate grid plane, except for the x-axis has become the real number part of this number in standard form. And then the imaginary axis here is your y-axis. So if I were to plot this complex number in this axis here, we would plot the real number in the x direction and the imaginary number in the y direction. Then we're going to look at how to find the absolute value of a complex number, and that looks like this. Absolute value of A plus BI. That's going to equal the square root of A squared plus B squared. And as we go through this, you're going to realize where this comes from. So we're going to actually graph it, and you're going to find it, and you ought to be able to physically see why we're using this for the absolute value. All right, and then finally, complex conjugates. So remember when we had 5 plus the square root of 3 in the denominator? Remember, you cannot have why can't I think right now? You cannot have a square root in the denominator. So let's say that I have, actually let's use the number that we had above there. So let's say we still have 2 plus 3i. So we'll use that same complex number we've been using. And let's just say that this is in a denominator. Well, I cannot be in a denominator because it's technically the square root of -1. So we're going to use complex conjugates in order to get rid of that in the denominator. And so a complex conjugate is just like we did with radicals, you're going to change the sign in the middle to its opposite. And so they come in the general form of, if you have a plus bi, then you're going to have a minus bi. It's that difference of two squares factor pattern, the plus minus pattern. All right, now, this is your visual vocabulary. So this is the whole set of complex numbers, a plus bi. This set of complex numbers is made up of the set of real numbers, that's an arrow, and the set of imaginary numbers. So if I had a pure real number, the imaginary part would be 0, and you'd just be left with a. So if we were looking at this complex number, 2 plus 3i, 2, if I had 2 plus 0i, then I would just be looking at the real number 2. If I were looking at just a pure imaginary, I would have 0 plus 3i, and so then it would just be 3i. Then the definition of the square root of a negative number. So and this is really the basis of where we started using imaginary numbers. So if you have the square root of a negative number, so I'm going to give it a number for you. So let's do the square root of negative 49. So this is saying that I can split that negative out of the 49, so I can split it up into negative 1 times 49. And then I can take those and split those into two separate square roots. So square root of negative 1 times the square root, well, that equals, times the square root of 49. Well, the square root of negative 1 can be written as I. The square root of 49 can be written as 7. And we don't write something I7 because remember I has all the properties of a variable. So we would actually write this as 7i. All right, let's go ahead and graph the following numbers. So I'm going to make this just a little bit bigger. Okay. So when I graph this number, I pretty much ignore the I. I'm going to graph the 2, which is the real part, in the real direction. So the real direction goes right or left. So if I have a positive, I'm going to go to the right, and negative, I'm going to go to the left. And then I'm going to graph the imaginary part. I'm just going to look at the coefficient only. I'm going to ignore the I. So if it's a positive coefficient, I'm going to go up, and a negative coefficient, I'm going to go down. So for this first one, I'm going to graph this one in red. So the 2 means I'm going to go right 2, and the 3 means I'm going to go up 3. So right 2 and up 3 would put me right here, and so this is where A is. Then B, I'm going to graph in blue. So for the real part 4, that's in a positive direction, so I'm going to go right 4. And the imaginary part for 3 is negative 3, so I'm going to go down 3 on the imaginary. So I'm going to go to the right 4 and then down 3. So then this is where B is. Then I'm going to graph 2, or C in green. So this one's missing its real part. So the real part is 0. So I'm going to go 0 right or left. So I'm not going to go right or left at all because I'm missing the real part. But I am going to go up 2. So I end up on the y-axis here, which is the imaginary axis only. And then finally my last one, I'm going to do this one in pink. So my real part is negative 1, so I'm going to go left 1 for that negative 1. But my imaginary part is 0, so I'm going to go 0 up or down. So I'm just going left 1, no up or down, so I'm actually on the x-axis, which is the real axis, and that's where D is. Now what I would like you to do is take what we just talked about. Actually, I'll do the first one with you. So let me make these bigger. Okay, so if we're going to take the square root of 12, it's no different than when we simplified radicals before. So I'm just going to take the negative out of the 12 and make it a negative 1. And then the 12 prime factors into 2 2s and a 3. Well, The two 2's I can pull out in front as a 2. The -1 gets pulled out in front as an I, because remember I is the square root of -1, and then whatever's left over, in this case 3, would stay underneath the radical. And so then this ends up being my final answer. So the square root of -12 is really 2I radical 3. So then I want you to try B, C, and D on your own. So pause the video and then restart it to see if you're right. Okay, let's check and see if you're right. So for this one, remember you can split that negative out. So the square root of 25 is 5, and the square root of -1 is written as I. And then for C, we can't take the square root of 7, so I'm going to split this out as the square root of -1 times 7. I can take the square root of -1 out in front as an I, but the square root of 7 has to be left underneath the radical. Now that I definitely has to come in front of the radical, because if I were to write this as 7I, it's really hard to tell, is that I under the radical or outside the radical? So we don't write an I after the radical. So then this is our answer for C. And then finally D, you have to explain why the square root of -64 does not equal negative square root of 64. Well, this, as you recall, can be broken into -1 times 64. -1 is I, and 64, square root of 64 is 8. Well, that does not equal what this is asking for. So the negative here is on the outside, so it's asking for the negative square root of 64, which is -8. And 8I does not equal -8. All right, then we're going to graph in the complex number plane, and we're going to graph and find the absolute value of each complex number. So for A, if I'm going to find the absolute value of this, remember that equals the square root of A squared plus B squared. And you're going to see where that comes from here in just a minute. So this is A plus BI. So A here is 2, and B, the coefficient of the I term, the coefficient here is -1. So A is 2, B is -1. So when we put this in to this formula, I'm going to put in 2 for the A and -1 for the B. And so I end up with the square root of 4 plus 1, which is the square root of 5. And so we're going to graph this. So when you graph it, you're going to take the A part, which is 2, and we're going to actually lay a distance, because remember that the absolute value of a complex number is the distance that number is from the origin. So 2 is 2 units to the right, because it's in the real direction from the origin. So I'm going to graph that as a blue line. So that represents the real number part of 2. Then this -1 right here for B is going to go in a -1 direction on the imaginary axis. So I'm going to graph that in green. So my green is -1, my blue is +2, and then this distance from here to here represents this absolute value here of 5. Now, Pythagoras' theorem says if you take the length of this leg and the length of this leg and you square them and add them together, that they will equal c squared. Well, -1 squared is 1, 2 squared is 4, 4 plus 1 is 5, this squared is 5. So this came from the distance of the hypotenuse on a right triangle. So the distance of the hypotenuse on a right triangle in the complex plane is where the absolute value of the complex number comes from. So you can physically see that here. All right, so then let's look at B, and then I'll let you do C and D on your own. So again, we're going to find the absolute value of this, which is the square root of a squared plus b squared. So a, this is my a plus bi. So my a is -3 and my b is -2. So my a is -3 and my b is -2. So I get the square root of 9 plus 4, which is the square root of 13. So if I were to graph this, this is going in the direction on the real axis, so it's going to the left 3. So I'm going to plot a line all the way from the origin to the left 3. So that represents right there the real part of that complex number. Then the b part, the imaginary part, is -2. So I'm going to go down 2 on the imaginary axis and plot that point. So that's -2. This is -3. And so then this distance here should represent the square root of 13, which it does. All right, so you do C and D on your own, so pause the video, do them, and then come back. All right, so for C, so recall that this is a plus bi. So my a is 1 and my b is 4. So I get 1 plus 16, which is the square root is 17. So there's my absolute value. Then my real number part, so my a is +1, so I'm going to go +1 on the real axis. My b is +4, so I'm going to go 4 on the imaginary axis. And so this represents my absolute value. And so my absolute value is the square root of 17. Then finally D. So for D, if this is a plus bi, then my a must be 0 plus bi. So when I take the absolute value of this, I'm really putting in 0 for A, but 3 for B. And I get the square root of 0 plus 9, which is the square root of 9, which is actually 3. So in this particular case, you get an integer, a real number, not a square root. So then we're going to graph it. I'm going to graph 0 as the distance from my real part, so I'm just at the origin. And then I'm going to graph 3 in the imaginary direction, so I'm right here. And then notice that my absolute value matches the only number that's there, and I can't make a triangle on this one, and so that kind of makes sense. All right, so then let's look at your third page of notes. So for these ones, we're going to find the sum or the difference. So I'm going to do the first two with you and then let you do the second two on your own. Okay, so be careful and figure out whether you're adding, subtracting, or multiplying. So because there's a plus in the middle, I can drop these parentheses and just line up like terms. So I can take this 7 minus 2i, which is this one right here, and I'm going to line these like terms up underneath here. So I'm really just distributing a 1 in there, which doesn't change anything. So I get a -3 and a positive I. When I add those together, I get a 4 and I get a minus I. And so that's my complex number in standard form. Look at B. So for B, I have a subtraction sign in here, and so technically that means that I have a -1 in front of those parentheses, and I'm going to have to distribute that -1 inside those parentheses. So the first parentheses, 1 plus 5i, I can just drop those parentheses because there's a 1 in front. But then the second parentheses, this negative 1 times 3 is going to give me a negative 3. This negative 1 times negative 2i is going to give me a positive 2i. So my signs changed. I had a positive to a negative and a negative to a positive, but only on the second parentheses. So I get negative 2 plus positive 7i. So pause the video and I want you to complete C and D on your own. All right, then for C, I have a negative to distribute. So I have 8 plus 6i, which that didn't change. But when you distribute the negative, you get a negative 8 and a positive 6i. So the 8's cancel and you end up with 12i. Remember, the variable string doesn't change when you add and subtract. And so that is your answer there. Then for D, with the plus in the middle, there's nothing to distribute. I can just line this up with this. So that's what I'm going to do. The first negative 3 plus 9i, and then the second negative 3 plus 9i, no signs changed. Add together, you get negative 6 plus 18i. Then we're going to move on to multiplying. So for example 6a, we have a monomial times a monomial. So remember, we're going to multiply coefficient to coefficient, like base to like base. And also remember that I acts like a variable, so it has all the properties of a variable. So 7 times 3 is 21. And then I times I is I squared. But remember that we know what I squared is. I squared, remember, has a value of negative 1 because I is the square root of negative 1. So square root of negative 1 times square root of negative 1 is negative 1. And so our final answer is negative 21. So as you can see, the I squared essentially went away, and then it changed the sign of the coefficient. So the coefficient went from a positive to a negative, and then the I squared went away. Why? Because I squared is negative 1 times that 21, so it changed the sign. What happens when you have a binomial times a binomial? Well, you're going to have to FOIL or double distribute. So I'm going to multiply. 4 times 2 is 8. 2 times 5i is 10i. When I do my second distribution, I'm going to line up like terms. Negative 3i times 4 is negative 12i. And then negative 3i times positive 5 is a negative 15i squared. So remember that this right here has a value of negative 1. So when you have negative 1 times negative 15, I can actually cancel this out and make it a positive 15. Again, why? Because negative 1 times negative 15 gets replaced with a positive 15. So now I'm just doing 8 plus 15. 8 plus 15 is 23. And then 10 and negative 12 gives you a negative 2i. The variable string doesn't change. And then that's it. That's in standard form. You try C on your own. We'll talk about D in a minute, but you try C on your own. Make sure you don't leave any I squareds in your answer, and then restart the video. All right, so I'm going to double distribute. Negative 4 times negative 4 is positive 16. Negative 4 times negative 5i is a positive 20i. Then I'm going to distribute. 5i times negative 4 is a negative 20i. And then 5 times negative 5 is a negative 25. I times I is I squared. Remember that I squared is equal to negative 1. So negative 1 times negative 25 is a positive 25. So this gets replaced with positive 25. 16 and 25 they add to give you 41. So I get a 41. And then these cancel out. So all I'm left with is a 41. So notice that these are actually conjugates of each other. It's the same thing inside the parentheses, but instead of a plus, we have a minus. When you multiply conjugates together, it gets rid of the I, which therefore gets rid of the square root of -1. And the reason for this is if either this or this were in the denominator of a fraction, we would multiply by its conjugate in order for the i's to disappear. So notice the i's disappeared. Let's look at some powers of i's. Whoops, I don't know why I just did that. Try that. Let's look at some powers of i's. So we already discussed that I is the square root of -1. But we don't write the square root of -1, we write I. So I has to be left as I. I squared, if you recall, is the square root of -1 times the square root of -1. So a radical times itself is the number under the radical, which in this case is -1. Then I cubed can be written as I squared times I. So I squared, if you recall here, is -1. So this is -1 times I, which gives us -I. So I cubed gets replaced with -I always. The last one really is I to the 4th. I to the 4th can be written as I squared times I squared. And again, if you recall, I squared is -1. So we have -1 times a -1 is a +1. So these are the 4 forms of I. I is written as I squared is -1, I cubed is I to the 4th is 1. Every other power of I can be written in one of these 4 forms. For instance, I to the 5th. Now, I love I to the 4th because it has a value of 1. So if I can get anything in terms of I to the 4th, that's what I'll do first. So I to the 5th can be broken into I to the 4th times I. Well, I to the 4th is 1 times I is I. I to the 6th can be broken into I to the 4th times I squared. Well, I to the 4th is 1 times I squared is I squared. Well, I squared has a value of -1. So your answer there is -1. So essentially, you are going to continue to go in these multiples of 4. So notice it went I, -1, -I, 1. I, -1. The next one is going to be -I, and then 1. So for instance, let's just keep adding on here. I to the 7th. Whoops, I'm going to do that in black. I to the 7th. I can break that into I to the 4th, because that's my favorite, times I to the 3rd. So that gives you 7. I to the 4th is 1. I cubed can be written as -I. Then we're going to do one more for these ones, I to the 8th. I to the 8th can be written as I to the 4th times I to the 4th. Well, I to the 4th is equal to 1 times 1 is 1. So as you can see, this is repeated in the same pattern of 4, and it will continue infinitely that way. So if I had I to the 28th, all I have to do is figure out how many groups of I to the 4th I have in I to the 28th. So note that if I had divided the 8 by 4, because I'm figuring out how many groups of 4 I have in there, 8 divided by 4 is 2. Don't I have 2 groups of I to the 4th? And it went in there evenly. So the number of full groups I have here, this is just going to have a value of 1. So like here, if I take 28 and divide it by 4, well, 4 goes into 28 7 times. So I would have 7 I to the 4ths here. Well, all 7 of those I to the 4th have a value of 1. 1 times itself 7 times is going to be 1. So if it goes in there evenly with no remainders, we have a 1. But what if it doesn't go in there evenly? What if I had I to the, let's do I to the 90th. So if I take 90 and divide it by 4, 4 will go in there. So 90 divided by 4. 4 goes in there twice. Bring down the 0. 4 goes into 10 twice with a 2. So we have a remainder of 2. So I know that I have 22 sets of I to the 4th, which all have a value of 1. The remaining 2 is I times I, which is I squared. So I to the 90th has a value of I squared, and we know that I squared is equal to -1. If I have I to the 123rd, if I divide this by 4, so I'm going to do long division off to the side. So let's do it over here. So 123 divided by 4. So 4 goes into 12 3 times. Bring down the 3. That means I have a remainder of 3. And so I've got 3 sets of I to the 4th. I don't have 3 sets, I really have 30. That technically should be 0 because it didn't go in there any times. Now I have a remainder of 3. So I knew that looked funny. So I have 30 sets of I to the 4th. So I have I to the 4th 30 times. Well, all 30 of these have a value of 1, but these remaining 3 are going to represent I cubed. So the remainder is what the exponent is for your I. Well, I cubed is equal to -I. So that's all you do. Okay, so what if I am dividing and I have an I in the bottom of my fraction? So I'm going to do A and B with you, and then you're going to do C on your own. So let me make these a smidge bit bigger. There we go. Actually, I can make it bigger. I don't need that much room. Okay, so anytime you have a complex number in the denominator, you want to use your conjugate. So the conjugate to 3 plus 4i is 3 minus 4i. What I do to the bottom, I must do to the top. So 5 times 3 is 15. 5 times -4i is -20i. Then I'm going to distribute the -2i. -2i times 3 is -6i. And then -2 times -2i times -4i. The -2 times the -4 is a +8. I times I is I squared. We'll deal with all that in a minute. Then I'm going to distribute the bottom. So let me use a different color. So I'm going to use pink. So 3 times 3 is 9. 3 times -4i is -12i. Then I'm going to distribute the 4i. 4i times 3 is +12i. And then 4 times -4 is -16. I times I is I squared. So these are going to cancel. And don't forget that with the I squareds, we can convert those I squareds to -1. So -1 times 8, this is going to convert into a -8. -1 times -16, this is going to convert into a +16. So up top, I get 15 minus 8 is 7. And then -20i and -6i, we're collecting like terms, so we only add the coefficients. The variable string doesn't change. So we get a negative 26i all over. And this is the great thing, we no longer have any i's in the denominator. We have 9 plus 16, which is 25. But the bad news is we need to write this in standard form. And so standard form requires that we break this apart into its real and its imaginary components. So what does that look like? So each one of these has to get divided by the 25. So you're going to break it apart that way. So I get 7, keeping the sign with the term, over 25. And then the 26i is negative, so I'm going to have minus 26 over 25. And the I has to get pulled out of the fraction. Strange but true. So I took the 7 and divided it by 25. Here we are. I took the negative 26 and divided it by 25. Here we are. And then the I gets pulled out of the fraction. If you can reduce these fractions here, you must, but we couldn't here, so this becomes our final answer. Now, there are a couple of ways that you could actually do B. So you could use the conjugate. I don't ever use the conjugate. I mean, you could multiply by the conjugate. The conjugate to this technically is negative 6i. And so multiply to the 6i, you're going to get negative 36 times I squared. So you would get negative 36 times I squared, which changes this into positive 36. But, and then what you do at the bottom, you do at the top. But if I have a monomial, I don't like to do that. So instead, I would prefer to not multiply if I have a monomial by the conjugate. All I need to do is get this I to become an I squared, because I squared is negative 1. So, and you're going to see on the answers her multiplying by that negative 6i, but wouldn't it be easier to just multiply by I and I? What I do to the bottom, I do to the top, because what that's going to give me is I times 4 is going to give me 4i, and then I times negative I is negative I squared. We'll deal with that in a minute. And in the denominator, won't I have 6i squared? Well, that I squared is equal to negative 1. So negative 1 times 6, this is going to get replaced with negative 6. And then this negative I squared here, this is negative 1 times a negative. So negative 1 times a negative is a positive 1. So this becomes a plus 1. So I'm going to rewrite this. I'm going to put the real part in front of the imaginary part. So I get 1 plus the 4i over the negative 6. So again, I took the real and the imaginary and I switched them around, so I have real plus imaginary over this negative 6. Now you know we can't write it this way. We've got to split it into the real and the imaginary. So we have negative 1/6, because the 6 is negative, minus 4/6 I. Well, I can reduce this 4/6 into 2/3. So my actual final answer is negative 1/6 minus 2/3 I. All right, so you try C on your own. Pause the video and see how you do. All right, so for C, we do need to do the conjugate because there's a plus sign down here, and so the conjugate would be 5 minus 4i. And so what I do to the bottom, I do to the top. And so I get 5 times 5 is 25. 5 times negative 4i is negative 20i. Then negative 4i times 5 is another negative 20i. Those do not cancel. Negative 4i times negative 4i is a positive 16i squared. We'll deal with that in a minute. Over. Then I've got 5 times 5 is 25. 5 times negative 4i is negative 20i. Then 4 times 5 is positive 20i. Those are going to cancel. And then 4i times negative 4i is a negative 16i squared. Now you can't cancel these because we have addition and subtraction outside of parentheses. You can't cancel these, so don't go and try that. So instead, these do cancel. The negative 16i squared becomes a positive 16i squared. The positive 16i squared, or just a positive 16. The positive 16i squared becomes a negative 16. And so, this 25 minus the 16 is 9. Negative 20i and negative 20i is negative 40i, all over 25 plus 16 is 3041. Now, of course, we've got to split the real from imaginary, so we've got 9 over 41 minus 40 over 41i. And that's all there is to the complex number system. Good luck with your homework. Ask me any questions you've got.